Welcome back, everyone. We're in Chapter 13 on chemical equilibrium. And Section 13.2 basically looks at specifically at chemical equilibrium. The word equal, of course, means same on both sides. So we need to find out what is equal. We're going to see that in all the examples that you've had up to now, I've always drawn a chemical reaction as happening from the left to the right. You have reactants on the left and an arrow that points to the right, and then you have products on the right. Certain things come together to make other things, and you have reactants and products. If you didn't know better, you would say, oh, all the things are coming together to make the stuff on the right. For instance, if I'm making peanut butter sandwiches, I take the 20 pieces of bread, I put them together two at a time with peanut butter, and I end up with 10 peanut butter sandwiches. What's happening really with chemicals is that it's random. It's random bumping together. There isn't a specific mind putting things together. I do believe God's involved with everything, but the chemicals themselves bumping around, it's a random event. And remember, you can make it go a little bit easier if you make it faster. If you heat something by putting in a Bunsen burner, you can get them to slam together faster, which means they're going to have more impacts. Some of those impacts are going to have enough energy to make a new bond, and you're going to end up with a product. Some of them are going to bump together, but never bump together strong enough to make a product. Or if they bump together strong enough, they're not going to be aligned properly so that they can make a product. And then in the meantime, some of the product is going to break apart back into reactants. Okay, so imagine that you put it together and it just breaks apart again. Certain things are going to break apart and come together many times during a certain amount of time that you're looking at it. So it's a lot more complicated than making peanut butter sandwiches, and it would be a lot easier if you just had a mind that's doing it. But since these are random events, many times you are not likely to get 100% going to product. You might get 50% of the time it goes to product. It's just as likely for it to go to product as it is to stay reactants. Or maybe you can get a little bit to go to product, but not very much. Or maybe you can get a whole lot to go to product, but not all of it. Okay? Maybe conceivably you could think of a situation where all of it would go to product. And I can imagine certain things. For instance, if you can put, let's say, acid on a piece of limestone and it bubbles, and the carbon dioxide gas bubbles away and goes out into the atmosphere, well, then that carbon dioxide gas is not there to go back, because all of the products would have to be there so that it could then be the reactants in the reverse reaction. Okay, so you can imagine that some cases you can make it go all the way to completion, but most of the time it's some percentage of product that you're going to make. That's another reason why the actual yield is always less than the theoretical yield. Just because the numbers say I can make 10 grams doesn't mean that all the molecules are going to actually bump together and make the product. Okay, so let's look at some of these. You'll see that there's a double arrow in this reaction. We've always had arrows that are simply single going in one direction, but now we do have a concept that some of this product is going to break apart again into reactions. So you have combination reaction going forward, and you have a decomposition reaction going backwards. Okay. Now you have no way of looking at this and guessing how much product I'm going to make. No way at all. You actually have to do experiments. You have to do many experiments on this and measure how much product you make over a certain amount of time under specific conditions in order to say, generally, you're going to have 80% of it go to product, or you'll have 40% of it to go to product. So what's going to happen is that often these arrows are going to be different lengths. You might have a large arrow going right where lots of product is being made, and then a little bit of arrow going left, which means that some of the product you make is going to break apart again. Okay? So you could imagine kids at a sock hop, and you have couples coming out to dance, and then the couples break apart and new couples come back. So you might always have a certain amount of couples on the floor, but they're always different kids. Or you might be a bus driver and one person gets on the bus and another gets off the bus, and you had 15 at the beginning and 15 at the end, but they're different people in the seats. Okay, so what you're going to see in terms of equilibrium is not whether it goes right or left, but if the rate of going right is exactly the rate going left, then you're always going to have the same amount of product. You'll always have 10 people dancing, you'll always have 15 people in the seats. So that amount of product or reactant doesn't change, but it's back and forth and back and forth. That's the idea of reversible. Okay? So if you're at equilibrium, what that means is the reverse reaction is going to be equal to the forward reaction. Okay? So if the rate of the forward reaction is getting slower, okay, let's imagine that we start with 100 cations and 100 anions. And if they bump together, they're going to form a salt. Okay? So what's going to happen? With 100, they start breaking down, because if I had 100 and 100, they're likely to find each other. Okay? The higher the concentration, the more likely it is that they can bump into each other with the right energy. But as I start making product, my reactants actually drop, because let's say I'm making peanut butter sandwiches. Once I make 3 or 4 peanut butter sandwiches, I only have a little bit of bread left. Okay, so the smaller the amount of molecules that are having to react, the less likely they are to find each other with the amount of because they could bump around for years without ever actually bumping into each other. They might miss each other over and over again without actually coming together. And then if they do come together, they might come together with not enough energy, or they might be aligned improperly, and so they don't slam together exactly right to make a lock and key and make a new combination. Okay, so you're going to get a drop here, and then eventually it levels off. Now here, okay, let's say that you have lots of combinations, and they're breaking apart. Okay, they're breaking apart. So it's going to first break apart. If you only have a little bit of product, it's not going to break apart very fast. But the more product you have, the more likely it is to break apart. Like if you have 1,000 products, some of those are going to break apart, and so it's going to get you're going to get a curve kind of like this. Eventually, they line out. That means the same amount of people are getting on the bus and the same amount of people are getting off the bus. Okay, so it's equal in terms of rate. The forward rate is equal to the reverse rate. If you're going to write down one note for this section, that's what you write. At equilibrium, the rate of production of product is going to be exactly the same as the rate of production of reactants. Products in the other direction. Okay, so as it goes from right to left, it's at the same fastness as it going from the left to the right. Okay, so if one person gets on the bus and one person gets off the bus at that same rate, you're always going to have the same amount of people on the bus. So the amount of product is always the same. Okay, so that's what this says. When equilibrium is reached, there's no further change in the amounts of reactant and product. Okay, you have the same amount of product, same amount of reactant. Okay, let's go back a second. In this case, you're going to have the same amount of products and the same amount of reactants. Your areas are exactly the same. In the second case, okay, you're going to have you might have a lot of product being made and a little bit of reactants being made. So in this case, your arrow will be more towards the right and a little bit towards the left. So you'll have two arrows, but one of the arrows might be big and the other one might be smaller. One might be long and the other one might be short, whatever you do. Here's a case example. For a reaction in equilibrium, hydrogen gas plus iodine gas can make hydroiodic acid. That's what that says. So in the forward, the hydrogen and iodine is forming hydroiodic acid. In the reverse, the acid breaks apart to form hydrogen and iodine. At equilibrium, once it's at equilibrium, the products and the reactants don't change. So let's say I made 80% of the hydrogen and iodine came together to make acid. You'll always have 80% acid, and you'll always have 20% of the product, of the reactants that have never come together or come together and break apart again. Okay, so you'll always have the same amount of people on the dance floor or the same amount of people on the bus. Okay, here's an example. At the beginning of a reaction, I have lots and lots of reactants and no products because I haven't done anything yet. I haven't made anything yet. Okay, so there's lots here, and in this short little space, maybe they can have enough energy bump into each other. It's crowded, and since it's crowded, they're likely to bump into each other. And if they bump into each other with enough energy and at the right configuration, then they'll form a product. So here you've got a little bit of product made. Okay, that's the blue and the white. A little bit of product has been made, but you've still got a lot of reactants. Okay, so you've got a little bit in one area, a lot in the other. Let's look at this one. Okay, you still have, I've got 2 whites and 2 blues and 4 products. Okay, I've got 4 reactants and 4 products, and so the likelihood of them coming one direction or the other direction is the same. I've got the same amount of product and the same amount of reactant, so the likelihood of them breaking apart or coming together could be about the same. Once I get lots and lots of product, see here I've got 6 product and only 2 reactant, it's less likely for the reactants to find each other. These 2 guys have to hit each other exactly strong enough and right at the right angle and right at the right configuration. And since all these other ones are in the way, the chances of these 2 get lower and lower and lower. So you're going to end up with maybe an arrow. Well, here it is actually. You're going to have a large arrow going to the right, a little arrow going to the left. And look here, you may eventually have the 2 slammed together, but in the meantime, these guys might break apart again. And so you might end up with reactants again. So what's happened is the same amount of product, 6 product is made, but these might be different molecules that are actually arranging. Different Legos have to come together to make them. This is equilibrium. Equilibrium means that the same rate of forward is the same rate as reverse. Okay, I'll try to answer your questions. I know this is a confusing chapter to a lot of people, but it's basically just how fast or how much is being made in either direction and how much is left over after you cancel out the left and right movements. All right, see you in class.